Hello, everyone. Today we're gonna present a joint webinar with a collaborator from University of Calgary, Mahmoud Nwer. My name is Ahmed Atiya, and I'm working at OptiWave Systems. The webinar today is about radio over fiber systems for cloud radio access networks. The webinar will include the following topics. First, we're going to give some information about radio over fiber in optical communication systems. Then my collaborator Mahmoud will describe the 5G front haul downlink transmitter block diagram. Then he's going to talk about the scheme he's using for digital linearization of the modulated signal. And then he presents the experimental setup and results. And I'm going to talk about the numerical simulations. And with that, we conclude the webinar. The questions could be directed to support@optiwave.com. So radio over fiber, basically a concept where you have the laser light modulated by a radio frequency, sinusoidal signal, which generates two tones at the carrier frequency of the light. And then this signal would be, or these tones would be modulated with information signal and carried over fiber or in free space. The radio over fiber communication systems is implemented in wireless communication systems for 4G, 5G, and then Wi-Fi, as well as in satellite communication, where the signal in the L-band in the range of 950 megahertz to 2.15 gigahertz is used, and in cable TV, where signals in the range between 54 to 870 megahertz modulate lasers at 1310 nanometers or 1550 nanometers. This again, the signal would be transmitted from a source central offices to the destination where through a fiber or through a space where an antenna is going to be used to transmit the optical signal after detection and conversion into electrical domain. The signal, the information of the signal is usually modulated using different modulation scheme which is available to the user. Some of them is like intensity modulation and direct detection, or can be used other schemes like QAM, OFDM, or BAM signals. So all of these kinds of modulation schemes are available to be used in the radio over fiber transmission systems. Now, in this webinar, we're going to talk about signals where we're having a bandwidth of about 20 megahertz and modulated into 30 gigahertz represents a millimeter wave, which is typically used for 5G communication systems. The work is being published in a journal of transaction of microwave theory and techniques just recently by my collaborator at the University of Calgary. And in here, we're gonna verify and use OptiSystem to simulate the transmission system and show you the results of this communication system. Now I'm going to transfer the presentation to my collaborator Mahmoud, who's going to talk about the theory and about the experimental setup.
Okay, thank you so much, Ahmed and Brian, for having me sharing this webinar with you, and this great opportunity for me to present our work that was done last year. So this is summarizes the whole work. Now we have the antenna that sends signals to 5th generation mobile station. The two green boxes here, the one underneath here is the baseband unit. That consists of few optical and electrical components, as I will explain later on. And then there is a remote radio head that's split apart by about 12 kilometers, and it contains photodetector and some electrical bandpass filter to choose the band that we need. So we named this one front haul, and it's a common known link because it's just facing the mobile station, and it's a downlink because we are sending the signal down to the mobile station. We use this link for the next generation, the 5th generation, because the next generation expecting that we will provide them with broader bandwidth that could reach to 500 megahertz. Now we need to make sure that at least we can provide 10 gigabit per second for each subscriber. In order to do that, we need to utilize higher band. So we are thinking about the millimeter wave that starts from 30 gigahertz to 300 gigahertz. The way of doing that, we can do it traditionally by using GAN oscillator, but then that one will include phase noise, and then if we use if we use copper cables to that, for that, it will have higher losses, heavier weight, and more noise. The fiber optics on the other side has lighter weight and less losses, something about 0.2 dB for each kilometer. And then it has a very compact and small size components. So just small size distributed feedback laser, and then 2 identical Mach-Zehnder modulators. You amplify the signal, you clean it, and you send it down to the photodetector. So the second slide here shows the digital predistortion block. So traditionally, if you have any input signal, and imagine that you don't have this copy right now, the link nonlinearity, and that's mainly because of the Mach-Zehnder modulator, will generate intermodulation distortion. Could be the third or fifth intermodulation distortion that you will see at the output. Now, if we look at the nonlinear equation right here, if you divide the output signal by the linear gain, you will end up with a nonlinear signal. And if it's really linear, you will just have just the linear gain, constant value multiplied by the input, and you will end up with a linear output. Now, if you convert two signals, we need the transfer function of our link to be linear so that you can get exactly or similar to the input signal that you send. In order to do that, you need the inverse of the transfer function of the nonlinear block. So that is done by the help of a memory polynomial model. So we have the input and output. We compare the input and output together, and we generate the inverse coefficient to generate by the end something called predistorted signal. This will cancel out any nonlinearity that could be generated by the nonlinear block. We have multiple iterations in order to minimize the errors between the input and output. So before we buy the components, we thought about doing some mathematical analysis and simulation. So the mathematical analysis that started with just a plane wave for the laser. And then we move, we know that the transfer function of the Mach-Zehnder modulator is just sine square. And we have, if you have sine square and there is a sine inside the sine square, then you need to break it down by using Bessel functions. So the fruit of this equation shows us that we have nonlinearity because of the Bessel function. And there are also images and some tones that you will see after the photodetector. So this is the power after the photodetection as a result of beating. Now, the spectrum right here to the right is actually from the OptiSystem. It was a very helpful software that minimizes the time and confirms the results before you start the experiments. The black curve right here, it's for the LTE signal that you use. It's 20 megahertz bandwidth, and it's a standard LTE signal. It's 64 quadrature amplitude modulation OFDM signal. So we sent the signal in the beginning at 2 gigahertz, and the output, so we have at 2 gigahertz, one of the images, and we have at 20 gigahertz and at 24 gigahertz, same signal. And then what we see here is spectral regrowth. This indicating there is a third order intermodulation because of the nonlinearity of the front hole. So the experimental setup here is the block diagram of the experimental setup. we just need to explain in this block diagram how the signal flows. So we have this distributed feedback laser that emits light at the C-band, and then we modulate this laser tone by sinusoidal signal. You can choose any carrier frequency you like. We choose 11 gigahertz here. And then at the beginning, you have to minimize the main carrier, reduce or suppress the main carrier by setting the DC local oscillator or the DC voltage to the minimum transmission point where you suppress the main carrier. Then you will end up with two main tones at the output. These two main tones are going to be modulated again by our baseband signal that's generated by MATLAB. Then you just load them in any transmitter. In our case here, we have the National Instrument transmitter. And then you set the carrier frequency or the mixer frequency. You amplify the signal by a linear driver, electrical power amplifier. Then you set it to the data max intermodulator. We named this one data and this one com. They are actually identical, but the difference is just setting the DC point. So this one has minimum transmission point, and the data, we set the biasing point to the quadrature point in order to reduce the nonlinearity of the max intermodulator. We amplify the signal, and then we remove any amplified spontaneous noise or ASC noise that's generated from the amplification process. So we send the signal down to about 12 kilometers of fiber, and then the output will see the beating takes place at the photodetector. Now, as we can see here, this is the spectrum after the second Mach-Zehnder modulator. We have amplitude modulation, which means that like double sideband modulation, the data will be around the main carriers, and there is also here around this one, but they are very small, so ignore them. And there is also same amplitude modulation about the second main tone. The beating that is happening between the main tones will be shown at the electrical domain right here. So we have one at FC, that's because of beating this one with the right and left side, also this one with right and left side. So we have almost 4 contribution, and then we have 2 contribution at this frequency that's beating the blue one with the one that's closer to it there, and this one with this. So we have similar contribution right here. Then this blue one is a result of beating F1 with F2. This can be seen output. If you have full span, you will be able to see all of these spectrums, all of these tones and data by the spectrum analyzer, as well as by the OptiSystem. So this is our setup in the lab. Starting by Teraxon laser. It's a DFB laser that has a line width of 200 kilohertz. We choose this one. I mean, if you get minimum line width, you will be able to get sharper peak and then better beating. The signal has a optical power of 35 milliwatts. Then it will go to the first Mach-Zehnder modulator, where we have the 11 gigahertz coming from the local oscillator signal, and then we bias the first or the comb Mach-Zehnder modulator by a DC supply. The signal will travel to the second Mach-Zehnder modulator, which is the data modulator, where we insert our data from the National Instrument transmitter, and then we set the biasing point to the quadrature point. The signal will be amplified by the EDFA and then cleaned from any SC noise, and then sent through the fiber optics pool of about 12 kilometers going to the photodetector. From the photodetector, we will have the beating signal captured at the VSA. So these are one of the spectrum that we started, is like preliminary results that we have before conducting the work, and we see here the comb-like peaks. Now this is as a result of external modulation. So we have the laser, and then we have an RF signal, and then we set the transmission point to the quadrature so that we have almost, we are not suppressing the main carrier here, so they are almost flat, not really flat, but we are not suppressing the main carrier, and the distance between each tone or each peak is 10 gigahertz. Here's also a spectrum from the optical spectrum analyzer. Here is the output from the the second Mach-Zehnder modulator. So we have two Mach-Zehnder modulators, and here we are suppressing the main carrier, and then we don't have data. So once you open or you switch on the data from the second Mach-Zehnder modulator, you see that a little tones or data is coming like amplitude modulation or double sideband modulation in the second figure right here. So we don't have data here, and the data is on in this figure. So these are the specification of our component. As I said, 200 kilohertz line width, C-band frequency of the laser, and it's emitting a power of 35 milliwatt. Two identical Mach-Zehnder modulators from OptiLab, and then you control, of course, the local oscillator frequency according to what you need, and then you will end up with two main tones at F1 and F2. They will beat together to produce the millimeter wave that you like. The LTE signal that we use has 64 quadrille-chambered modulation of the signal, and then we also transmitted 256 QAM as well, as I will explain later on. The two Mach-Zehnder modulators that we have has a half-wave voltage or switching voltage of 5 volts. You can use different bandwidth of the signals that you like. Now we use 20 megahertz signal, because that's the maximum bandwidth for LTE signal. And then you can also tune or choose the carrier frequency of your LTE signal. Because of the limitations of our equipment, the NI has a maximum reception bandwidth or frequency of 26.5 gigahertz. So we decided to use 24 gigahertz instead of 30 gigahertz, and just to give an idea of the near millimeter wave signal, how can we linearize it? Okay, so the length of the cable, the length of the fiber optic is about 12 kilometers, and it's single mode fiber. We made sure that we keep the optical power before the photodetector to about 9 milliwatts, and then the optical bandpass filter, of course, to clean the noise. So it's a 24 gigahertz, as I said, near millimeter wave frequency. So these are the spectrum and constellation at the output. Now the blue one right here shows that there is a nonlinearity, quite a bit, about 12 dB nonlinearity. This will cause the constellation to looks like that. It's not confined very well, and the EVM is high, something around 6.2%. And then after applying our model, we were able to suppress or remove this nonlinearity by, if you look at the red curve right here, and then it's more cleaner. And the second one with the digital predistortion. So here it's about 1.9%. And this is 64 QAM. So we thought about increasing to three aggregate of 20 megahertz. So the total is 60 megahertz. By the way, I need to say that there is 100. So the theoretical or the peak bit rate for each 20, if you use 64 QAM, is 100 megabit per second, and then the total will give us like 300 megabit per second. But this is the peak. This is like the theoretical value of the bit rate. But if you talking about the practical bit rate, maybe you will get something around 70 megabit per second, because you will utilize the other slots for pilots or other functions. So here is before before the digital predistortion, here is after, so it's cleaner. However, it's not as clean as the 20 megahertz because of you know, the memory effects. Now we used even higher constellation, the 256 QAM, and it shows that we were also, the model was able to remove the nonlinearity and reducing the EVM, the error vector magnitude, from 8.3% to about 3%, and so we are here below the maximum threshold that was set by the LTE standards. Okay, now I'm done from my side, and we will transfer the screen to
Okay, thank you, Mahmoud. Now I'm going to talk about the simulation part. In the simulation, to represent the schematic, the block diagram, which is envisioned by and demonstrated experimentally by our collaborator Mahmoud at Calgary University. This is the project layout, which has all components in the design, and I'm going to show you the project in a few minutes. But at the beginning, we're going to talk about the component used. So this is the DFB laser, which is set up the carrier, and this is the first modulator, which is the comb modulator, which is basically creating the RF radio over fiber tones using a sinusoidal wave. It's sitting at 11 gigahertz. And this is the second modulator, which carries the information, which is in our situation here is data. The data is generated using a bit error rate tester, which generates a pseudo-random bit sequence. This pseudo-random bit sequence goes into the QAM sequence generator, where generates the QAM 64 QAM signal, or the 256 QAM. And this QAM signal is used to carry on each of the M carrier, subcarrier, and we have 1,200 subcarriers here. Then passing through to the second modulator, which modulate the tones with the data information. And then at the output of the modulator, the signal is transmitted through optical fiber and then amplified as a pre-amplifier in front of the detector and then you place a band pass filter here to remove as much as possible from ASC to improve signal to noise ratio at the detector. And then the signal is detected. Here we have square law device which do the beating as explained by Mahmoud, and then eventually goes to the OFDM demodulator to extract the subcarriers, its signal on the subcarriers, and then goes into the QAM decoder to get the data, this bit sequence, and the bit sequence goes back to the BERT, or the bit error tester, where bit error rate is calculated. Now in this figure here, you can see the tones, the sinusoidal tones created across the carrier, which is the light carrier around 193.1 terahertz, and this is the carrier at 11 gigahertz away from it. And then at the output of the second modulator, you have the tones with the data on it. And here you can see the visualizer. We use an RF spectrum analyzer at the output of the detector to look at basically the beating which occurring in the detector, and then the information. Now, if you zoom on these locations, as explained by Mahmoud, all these frequencies, you can see here the RF spectrum of the data, of the modulated data. And you can see this is the pedestal of the spectrum, which is created due to the nonlinearity. And with the scheme he is creating for linearizing the channel, you can get rid of it and then improve the performance of the system and reduce the error vector magnitude to the standard levels or below standard levels to allow the transmission. Now I'm going to move into the project layout, which is you can see here in this project layout here. the components which is designed in the OptiSystem. This is the laser, and every component here in the project layout. If you click on any component, basically, you can access the parameters of that component, and then you can set up the, for example, for this laser, DFB laser, you can set up the wavelength, you can set up the power level, the line width of the laser, and can set polarization, you can set the noise levels, and so on. For example, the sinusoidal signal here, you can control the tone frequency. Here it can use 11 gigahertz. You can control the amplitude, the bias of the signal. For the modulator here, you can set up, for example, the voltage, the bias voltage, and then eventually control if you're gonna have minimum bias, DC bias at 0 to minimize the carrier, or you wanted to have a linear modulation, which is at the quadrature voltage level. Any component here, if you click on the help button, you're gonna see the data sheet of that component basically, and it explains, give you more details about every parameter used in the component and the theory behind the component, which describes all the functionality of this component. Now, the fiber, for example, here, the fiber, you have the parameters. You can set the attenuation, you can set the dispersion, you can set the slope, you can set the BMD and the fiber parameter, which is not necessarily for low frequency rates, which is in this 100 megahertz regime. And then you can control the nonlinearity parameters and so on. In terms of the QAM here, for example, the QAM, you can set up the QAM. We are using here 64, so you can have or you have to have 6 bits per symbol. If you are using 256 QAM, then you can have 8 bits per symbol, and then you have flexibility to use user-defined IQ map and have flexibility in the design. For OFDM, you can control the number of tones, the subcarriers, and you can control what is the location of the subcarriers. You can control the average power of them, of each one, and so on. Now, once you set up the project here, one parameter you can control from something called global parameter, where you control the number of bits generated by the BERT here. So you have in this simulation 65,536 bits, and each bit have 256 samples. Now, as you see, the bandwidth of the signal is 20 megahertz, and now this bits will gonna transmit through the QAM, converted into the QAM signal, and then carried over the subcarriers and transmitted over the fiber. Once you do the calculation, it depends on the complexity of the calculation. Then the project will take certain time. In this project, I ran it ahead of time to save the processing time, which took about 7 minutes, 48 seconds to run this project. Now, you can have in an OptiSystem in the library, component library, as you see in this section, different directories. One of them is the visualizer directory, and in the visualizer directory, you can choose the type of visualizer you can use. In this scenario, we used, for example, spectrum analyzer, OSA. We used RF spectrum analyzer. You have other types of visualizers, which you can see in the visualizer in the directory for optical visualizers or electrical visualizers, like eye diagram, bit error rate, constellation diagrams, oscilloscope, and then you can have binary visualizer to look at, for example, the binary bits which is coming in here. So you have lots of flexibility of the system to look at your signal, to visualize it. The process of the calculation of visualization is there is some webinars available at OptiWave website where you can take a look and get more information about the process of calculation and enabling the visualizers and setting up the visualizer and so on. Now, the calculation process, if you run the calculate button here, you can see the process calculation. There's different options to calculate the project. The one thing which I wanted to mention here is some option is called calculate multi-thread all sweep iterations, and in this option, if you have a multi-core, for example, computer, you can speed up the process when you have sweeps in your project. If you want to sweep parameters in the layout, you can speed up this project. Now, the project, again, I did the calculation ahead of time, and then here, if you can click on the project visualizers, you can see, for example, this is the sinusoidal signal across from the carrier at the wavelength which is set up by the laser. In our scenario here, the laser wavelength is around 53 nanometers. Now, if you click, for example, look at the output of the modulator after you carry the data, you can see here the data are created across the tones, and it's similar to what Mahmoud shows in the experimental setup. Now, if you look at, for example, RF spectrum analyzer output of the detector, you can see the spectrum at different tones. Here you can see around, if you zoom the spectrum, you can see the figures as we showed you the spectrum which is located at this tone here. As you can see here, we have the project layout. You have different pages here for reports, for script of this project, where you do, for example, use this script to do data processing, post-processing, or you can, for example, create a script for the project which you can transfer it to some other users. Now, in this window, we have this project browser. If you click on any of these components, you can access it from here. So this is the OFDM demodulator. Now, OFDM modulator, if you look at the graphs in here, you can look at the constellation. The constellation, which is basically, if you click on this constellation here, you can see basically the constellation generated for the signal of the 64 QAM. Now, the same thing you can do for 256 QAM, and repeat the measurements and verify your basically design before conducting the experiment, and then compare the experiment with the simulation, which in principle should match as the software OptiSystem in the models used are as accurate and representing the devices in the market. With this, I conclude the presentation, and I'd like to thank our collaborator, Mahmoud Nwer from Calgary University. And if you have any question, please pass them to support@optiwave.com. And here's the emails of Mahmoud and myself. Thank you very much for listening, and hopefully see you sometime later in another webinars.